All right. So we left off at 16a. I believe we did that last time.
We did A, B, and C, I think.
We didn't do B. And
Or
there's one reason I know for sure. And that's because B has a typo in it. This is the way she printed it. Teacher, male or female?
female.
Okay. The way she meant to print it was like this. The only reason I know is because I looked at her key. Now notice the difference. In the top formula, the 2x plus 4 exponent really only applies to the 1. It does not apply to the e. And of course, 1 to any power is 1. So it's going to make quite a big difference. Whereas in the second row, when I put that 1 over e in parentheses, now the 2x plus 4 applies to both the 1 and the e.
Okay.
That's what she meant, was the second one. Now how else can I write 1 over e? What's a way to write that with exponents? In other words, if I said, what's a way to write square root of x with exponents, you'd say x to the 1/2, right?
Mm-hmm.
What's a way to write 1 over e with exponents?
E to the negative first. Or negative 1.
Good. And then all of that's being taken to that. In other words, the problem actually is a much better problem this way. Now, how do I handle this double exponentiation on the left side of the equation?
You gotta make both sides equal to each other, like the base.
First of all, you gotta combine those exponents to come up with e to a certain exponent. How do I do that? In other words, what is x raised to the a power all raised to the b power? How do you handle it when you have double exponentiation? What do you do with the exponents?
You multiply them.
All right, good. That's what I was looking for. Multiply the exponents, what do I come up with?
Negative 2x minus 4.
Hold on. E, don't ever forget the base. The base moves forward. So you have e to whatever exponents those multiply to. So what do you have? E to what?
E to the negative 2x minus 4.
Good. That's still equal to e to the 7x. And now what's the most important thing is we've got the same bases. One is to one exponent and the other is to a different exponent. So what can I say at this point in time?
That negative 2x minus 4 equals 7x.
Yeah, the exponents have to be equal. It's the only way this can be a true statement. Now solve this.
Okay, you add 2x to 7x.
Just read the next line to me.
Negative 4 equals 9x.
And now the final line.
X equals negative 4/9.
Got it. All right. Now, oddly enough, if you take her representation here, you actually get a different answer. I get 1 equals e to the 8x. And that's a completely different answer than the one we got there. So that's a typo for sure. Let's look at, hold on a second. Looks like I'm missing, there, let's look at C. What's the first step here?
1 to subtract 3.
Okay, so I'm going to get rid of that and turn that into a 2. What's the next step?
It's a times 2 by 2.
Multiply both sides of the equation by 2. It's not just the 2 we're doing, we're multiplying the left side also. But when we multiply the left side by 2, it gets rid of that. Multiply the right side by 2, it becomes 4. Now, just because I got all this scribbling, let's see what we got left. Now what's the next step?
Take the square root of both sides.
Good. Read the next line to me.
X plus 2 equals plus or minus 2.
Good for you. 90% of my students will forget the plus or minus sign. And it's extremely important. Now what's the last line?
X equals 0 and X equals -4.
Okay. Good. So here we have 1/3 E. And here they use parentheses when they don't even need to. In other words, I don't need these parentheses. It does not change the meaning of the equation. If I took them away, it would still be e to the minus 4x. First step?
Subtract 1 from both sides.
Next step?
Multiply each side by 3.
And now we have e to the minus 4x equals 15. Now what's the next step?
You take the log of both sides.
What kind of log?
It doesn't matter.
Actually, in this case, it does. Most of the, you're right. It really doesn't matter. You'll come up with the right answer regardless. But start thinking natural log. Natural log is the log of higher mathematics. When you get to calculus, everything's going to be natural log. Okay? And there's one huge advantage of taking the natural log here of both sides. And that is the natural log of e is 1. Okay? So I'm going to get a solution that doesn't have natural log divided by natural log. What's the next line now that I've taken the natural log of both sides?
Negative 4x equals natural log of 15 divided by 1.
Well, okay, this is the next line. In other words, what we've done is we've taken the exponent, we moved it down to there, and then that's 1. So the left side turns into minus 4x. As opposed to if we'd have taken a log other than natural log, we would have still have log on both sides. So this simplifies it a little bit, okay, by using natural log. It's rare that it matters. Usually you can take any log you want. But notice this answer is a little bit prettier than if we'd have used another log. If we'd have used another log, we would have had log of some number divided by some number times log of another number. So this is as concise as you can get. And notice what that is not. That is not the natural log of 15 divided by minus 4. That's, well, what I meant is the minus 4 is not in the argument. This is the natural log of 15, that quantity, that number, divided by negative 4. Now, is there a reason that E and F are missing? Because I have them on my key.
I have no idea.
Now let's go to the key. So we want to do 16E. Hold on, maybe I have to double click that. Yeah. 16E. I'm going to write it, and then we're going to do it. I don't really want you to be looking at the key while we do it. These are key problems here. I'm not sure why they were blanked out, but nonetheless, we'll do them. Can't imagine that you don't have to know how to do this problem. So the way to do these problems, these are log equations, is to first of all use your rules of logs to condense this. If I condense this into a single log expression, what would it be?
Log base 2 of x times x minus 2.
Yeah. Let's go ahead and multiply that out. So x squared minus 2x. That's equal to 4. Now, what can you say? In other words, the way to solve log expressions, or equations, excuse me, in this case is to turn it into an exponential. Well, how do you turn this expression into an exponential expression?
2 to the power 4 equals
Yep.
x squared minus 2.
Yep. The way I always think about this is it's the number on the far left raised to the power of the number on the far right equals the argument. Okay. Now that gives us 16 equals x squared minus 2x. We'll move the 16 to the right side because it's a quadratic. That's what you always do, is you put 0 on one side and that on the other. Now, does that factor? Gosh, it doesn't. Ah, come on. No wonder she blanked them out. She didn't mean to give us one where you had to use the quadratic formula. That's ridiculous. Am I missing something? What are factors of 16? 16, comma 1, 8, comma 2, 4, comma 4. That's it. No? Yeah, 2, comma 8's the same. None of those subtract to the number 2. That being the case, we would have to use the quadratic formula to solve this. And we can do that. In other words, x, do you know the quadratic formula?
Not memory very well, no.
Okay, I can give it to you and we could come up with a solution. Wow, cannot believe she did this to you. Whoever was putting this sheet together was really crazy. because if they'd used something that was reasonable, we could have illustrated a very important principle here. And that is, you cannot violate the domain. Let's talk about this a second without going through all of the arithmetic. Quadratic formula is going to produce a positive and a negative answer, correct?
Yeah.
It always does. Well, the negative answer violates the domain of that. You cannot take the log of, not only can you not take the log of a negative number, you can't take the log of 0. You can only take the log of positive numbers. So when we get through with going through the quadratic formula and we come up with 2 answers, we've got to dismiss the negative answer. In other words, you throw away the answer that violates your domain, and you keep only the positive number.
Okay.
Okay? All right, let's... I am at least beginning to see a rhyme and reason why these were blocked off. And it's because they're not good problems. I mean, E is a great problem. Let's look at her solution. You can see the problem here where I'm pointing?
Yeah.
All right, she's done it exactly the way I did it. She gets the same quadratic. Then she goes ahead and goes through the arithmetic, and she comes up with 2 answers. 1 plus or minus the square root of 17. Well, the 1 minus the square root of 17 is a negative number, so she doesn't show that being crossed off, but when she puts a rectangle around the 1 plus root 17, she's showing you that the 1 minus doesn't, that's extraneous.
Okay.
Here's my objection. This is illustrating a brand new point about logs, and that's solving log equations. Why would anybody in their right mind not make this factorable so that you did not have to go through the quadratic formula to come up with an answer? Sorry, it's my pet peeve, but
You're good.
I'm continually amazed that math starts every major subject out with almost the hardest subject of the year for that subject. And they do it with Algebra 1, they do it with geometry, they do it with Algebra 2, they do it with pre-calc, and they do it with calc, and they do it with trig. Every single new topic in math, they stick hardest problems right up front. Just, I guess, to demoralize people. I'm not sure. All right. What can I do here?
Add or subtract 4.
Okay. So that leaves... Now what can we do?
The negative 1 to the power of 3.
Well,
Or
you know what? Whenever I'm trying to solve a log equation, I'm trying to isolate the log term. Because I know if I can isolate that, then I can go from there. Always. So let's divide both sides by -1. That gets rid of this pesky negative sign. Okay?
okay.
Now, I have a log equation I'm trying to solve. Remember that when you have log equations you're trying to solve, at some point in time you convert them to an exponential expression. Let's do that. convert this to an exponential expression. Remember, it's this base raised to this power equals whatever's in the middle. So what's this base over here?
10.
It's natural log. LOG without a base would be base 10. Natural log is E.
E.
I know E is a number you're relatively new to, but trust me, it's the second most important number in all of math after pi. And it's a lot like pi. It's a number. It's not a variable. It's a number. And it has a value that's irrational and goes on forever without repeating. And it's approximately 2.71. I think the third decimal is 8. But it goes on and on forever. The most important part is that you know that it's approximately 2.71. Okay? And it's an extremely important number in a lot of higher mathematics. So you get e to the minus 3 equals 6x plus 2. So how do I solve this?
E negative 3 minus 2 equals 6x.
Equals 6x. Okay. No, that's a good step. Subtracting 2. In other words, I'm trying to isolate the x. So when I'm trying to isolate the x, I want to get rid of the 2 and I want to get rid of the 6. And you get rid of the stuff that's being added or subtracted first. So now x is going to be this whole expression divided by 6. And that's what x is. And in case you're wondering, you can get that number out of a calculator pretty easily. What kind of calculator do you have, Nicholas?
TI-84.
Okay. You know how to take e to the minus 3 power?
Yeah.
Okay. You got to find the key that's the e key. And then it's basically e raised to the minus 3 power. Use that raised key right there. Alright, and that's some decimal, and she told it to us. And the only reason that I think it's important to go over some of these is because I think that they're very instructional. And I'm not sure she intentionally meant for us to not find, like some of these are really important stuff that I can't imagine she wants us to skip. And 17 is another one that was left blank on the original that I don't want to skip. It's important to know how to do this. Complete the square and find the vertex. Alright, completing the square. First of all, this is a quadratic. You know, what's the shape of a quadratic?
A parabola.
Correct. It's either a parabola pointing down or a parabola pointing up. And you have a standard vertex format for a parabola that's very much worth memorizing if you don't have it memorized. That's that. And the reason this is so valuable is because H and K are the vertex. And so if you have a quadratic in vertex format, then you immediately know the most important point on that parabola, which is the vertex. There's very few other points that are even worth mentioning, but the vertex is huge. Knowing where the vertex is gigantic on any quadratic. So there's a huge reason why we have what is called the Vertex Form Map. So the idea is to take this format, which is more of a standard format, and convert it to vertex format. Well, the way you do it is a process called completing the square. And the first step of completing the square is putting parentheses around your terms that have x in them. Now, I haven't changed anything by doing that. But you cannot complete the square until the x squared term has a coefficient of 1, not 3, or 2, or 7. Got to be 1. So the way I get it is to factor out the 3, leaving this. Then I'm going to leave room to complete the square. I'm going to complete the square in this area right here. And I still have my plus 12. Okay? Now, the thing to always pay attention to whenever you're completing the square is that when you go from row to row, you do not change anything. I'm not attempting to change this equation. I'm merely attempting to manipulate it so that I get closer and closer to this format over here. And the way you do that is by completing the square. Now, do you remember how to complete the square?
Yeah.
How do I complete the square inside the parentheses only?
You I have no idea. I'm just blanking out.
Take half of the coefficient of the x term. What's half of this?
1.
Then you square that. Still 1. And you add it to the blank spot where I left room. Now, when I just wrote a 1 in there, I changed the expression. It's no longer the original expression I had. So if I want it to be exactly the same as the original, I got to counterbalance that. I got to subtract the amount that I just added to the same side of the equation. Well, how much did I just add?
1.
Not really. I added 1 times 3.
So 3.
3, which means I got to subtract 3. Now, this is identical to that. And I'm checking at every single step of the way so that I make absolute certain that I have not changed anything. Now, I can put it in vertex format. I get y equals 3, and the fact that I completed the square in there means that I can show it as a linear term, x minus 1 squared. You're always going to be able to do that when you've completed the square. The whole purpose of completing the square is so that you can show it as a linear term squared. Then I combine those two numbers, get plus 9, and bingo. There's my answer. And it's in vertex format. Where's the vertex?
1, 9.
Good. So that's how you complete the square. And this was a difficult one. I would have rather seen a simple one first. And again, I'm beginning to think that whoever blanked these out did it for a reason, and that's that they were giving you the hard problems before giving you easy problems. Now, maybe you've already had the easy problems. I don't know. Maybe we shouldn't even be going through these, but here, we're now on 18. Hold on, I'm just curious as to how she did this. Wow. What the heck? Her key is very, very strange here. To get to this answer that we got to a little differently, she did some weird stuff here, which I'm not quite sure of why. That's okay. So 18, let's make sure she has an 18 on her original quiz. It's funny how long it takes this program to switch. Hold on. Why isn't it going back to the original problem? Okay. There we go. It's clicking on the wrong thing. I guess it didn't like me clicking on recent documents. It made me click on the tabs at the top. Alright, I guess I can close that out if it doesn't do any good. Now let's go down and see if she's got an 18. No, she doesn't. She doesn't have, look at how many are missing.
Yeah.
Well, shoot. I don't know if they're missing on purpose or not.
I think they're on accident, because I kind of have the same ones missing on mine, too.
Okay. And I'm game for anything. We can go do each one of them. I mean, you've got 2 hours scheduled. Do you have school next week, Nicola?
Yeah.
So you're getting new material next week.
Uh-huh.
Well, that's going to matter. I think our best bet here is to do all of the ones that are not missing in our rest of our period of time.
Okay.
I think there's a good reason why they're missing. I think they're missing on purpose because they're extra difficult, which I don't have any problem with, but they may have been left out on purpose because of that. So here's what I think we should do, is do the ones that are visible, and then if we still have time at the end of the session, we'll go back and we'll do the ones that we're missing, starting with 18.
Okay.
Does that work?
Yeah.
Okay. I personally like doing hard ones, but there's some logic to why somebody had those missing. What's this equal to?
4x squared.
Hold on, what are you going to do with the exponents?
Add them.
Okay, what is 1/2 plus 1/3? Don't give me a decimal answer. Convert, find a common denominator, add them, and give me a fractional answer.
5/6.
Well, yeah, okay. So, whoops. So, to the 5/6. Now, it's worth noting here that this 1/2 does not affect the leading 2, nor does this 1/3. That 1/2 is to the x term only. So the way we handled this was multiplying the numbers together to get 4, and then multiplying x to the 1/2 times x to the 1/3 to get x to the 5/6. Okay? Always remember, when you have an exponent, it only applies to the thing that is beneath it, unless there are parentheses. If I put parentheses around that, like that, well, now the 1/2 applies to the 2 also. So this parentheses is big. That's why it was a typo on that one problem, is because she didn't have parentheses and she meant to. All right, here, let me write this one so I can expand it. That sounds like a dog on your end.
Yeah.
Just because its bark was different than the 2 dogs I have on my end. The pitch of it is different. All right. I don't really need this dot. I know that everything in the numerator is being multiplied together, everything in the denominator is being multiplied together. However, the way I want to attack this problem is I want to do all the numbers first and then all the variable x second. If there was a variable y, I would do it third, and if there was a variable z, I would do it fourth. In other words, the more variables don't make the problem more complicated, they just mean there's extra steps. So let's do the numbers first. What's 6 times 9 divided by 3 times 2?
54 divided by 6.
Okay. I'd rather see you do that a different way. In other words, what I'd rather see you do is, that's 6, and now that 6 cancels that 6, and the answer is 9. And I never dealt with a number greater than 9. The way you did it, you deal with a number 54. Well, when you deal with bigger numbers, you open up more opportunities for mistakes. So my general rule of math is always, if you have a chance, reduce before you do any math. Simplify first. By simplifying, you deal with nothing but small numbers. So 9 is the number part. Now, in the numerator, what am I going to do with the x's?
Find a common base for the...
Okay, so let's do it like this. Let's handle the x's in the numerator first. Okay, what's that come out to be?
X to the 7/6.
Okay, so we got x to the 7/6 there. And in the denominator, what does x come out to be?
7/3.
Yeah, good. Better than 2 1/3. Proper fractions don't really work very well. They shouldn't really be called proper, because improper fractions are much better. Always better to have stuff in a ratio than a proper fraction. Now, how do I do that? In other words, I'm not done yet. I've got a common base of x being divided by a common base of x, only I got different exponents. So what do I do with the exponents?
You make them have a common base as well.
Well, let's answer this question over here. It's not a common base. What do you do with exponents when you're dividing?
Multiply.
Hold on. I'm dividing the base. What am I going to do to the exponents?
Make them the same.
Subtract. when you're dealing with the rules of exponents, here's a really good way to memorize it. When the bases are being multiplied, you're going to do one level less with the exponents. You're going to add them. When the bases are being divided, you're going to do one level less with the exponents. You're going to subtract them. And when the bases are being double exponentiated, like this, you're going to multiply them. Multiplication is one level less than exponentiation. So if you can always remember that what you're doing with the exponents is always one level less than what is being done to the bases. So what is 7/6 minus 7/3 equal to?
Negative 7/6.
Good. That's my new exponent to a single x. So that would normally be my answer, but every teacher I've ever run into in Colorado has kind of a hidden policy that you never give answers with negative exponents. So how do I turn that into a positive exponent? What do I have to do to make that a positive 7/6? Put it on the other side of the fraction bar. That's it in a nutshell. Now, you might ask yourself, what fraction bar? I didn't see a fraction bar. But in reality, there was a 1 under that. Okay? So the x to the minus 7/6 went on the other side of the fraction bar, so it went to the denominator, and the 9 stayed in the numerator because the minus 7/6 didn't have anything to do with the 9. Okay? But here is our answer, and we have nothing but positive exponents, which they almost always won. Same number as I had here. If you put, same exact expression, it's just one of those conventions in math where they prefer you to have everything with positive exponents. Actually, I think it's just an exercise to make sure you know how to handle negative exponents. All right, let's look at I.
We did I last time at the very end.
I remember doing I. How did we do it so much out of order?
Cause I think it was supposed to be our last one before my mom made another one. So.
Okay. Yeah, because I was just going to say, this looks very familiar. I just assumed that I must have done it with a different student. Yeah, because it's hard for me to keep track. I frequently run into students who are in the same class or the same school, and they have the same kind of problems. And remembering which student had which problem is beyond my capability. So. All right, I don't ever remember doing this one, so let's do this one. What do I have to do? Oh, hold on. Let's see. Did I miss the rest of an equation? No, it's just simplifying the expression. Okay. How am I going to subtract these two fractions?
You gotta just simplify the bottom parts first.
Okay. Tell me what I should write over here for a denominator.
X minus 3 and x plus 2.
Good. Glad to see your factoring skills are good. What about over here?
X minus 3 and X plus 3.
Now, what is a common denominator?
X minus 3.
No? When you're subtracting fractions, how do you find, let's talk about that. How did you do this problem right here? How did you get a common denominator?
I found, 2 times 3 is 6.
Yeah, okay. So one way to get a common denominator is just to multiply the two denominators together. Okay? But you don't always have to do that. That's not always necessarily the easiest way. What's the common denominator between those three fractions?
I don't know.
It's 24. I don't have to, if I multiplied all three denominators together, I would get 48, which is a common denominator, but it's not the least common denominator. I'm looking for the least common denominator. Well, the way I find is the easiest way to find the least common denominator is to take the biggest one and start increasing it by factors of 8 and see where you have to stop before the other two terms divide evenly into it. Bingo. 24. 2 divides into 24, 3 divides into 24, and I know 8 does because I'm going up by 8ths. So that's the way you find a least common denominator. You don't always just multiply everything together. Okay, what I'm looking for is a denominator, the smallest one possible, where all three denominators divide into it evenly. Well, let me suggest what that is here. There is my least common denominator. Now, it may look like I multiplied everything together, but I really didn't. Notice that I didn't multiply the x minus 3 times x minus 3 twice. I only did it once, because that's all that was necessary. Now, how do I know this is a least common denominator? Well, if I divide this least common denominator by that term, I get x plus 2, whole number. If I divide this least common denominator by this term, I get x plus 3, a whole number. That tells me that I've got a least common denominator without having more than I need. In other words, if I were to just multiply the two denominators together, I would have x minus 3 squared, right? I don't need x minus 3 squared in this least common denominator. I need it to be least, not most. Now, the question is how do you get this term and how do you get this term?
You times...
Go ahead.
You times 4 by x plus 2.
Let's start on the top left. Let's work from left to right.
Okay, then 3x times x plus 3.
Good. So I'm going to write it like that before I do anything else. Just the reason I write it like that is because now I can check really quickly whether I've changed that fraction. I do not want to change that fraction. And the way I can check is that would cancel with that, and I'm left with exactly what I started with. So there's a really big advantage in writing everything out without factoring or without foiling stuff back together again or anything. In fact, a general rule of math is do not multiply factors back together again. Leave them in factored condition. And the reason is that, gosh, we don't know what we might have to do next with this function. Maybe we'll have to multiply it by x minus 3, and then we're much better off having these terms in factored state rather than non-factored. So I also can easily check that term there to make sure that it's the same as that. In other words, if I run a line through x plus 2 and x plus 2, I got the same thing I started with. So this might seem like trivial steps, but I tell you what, you won't make any mistakes by doing it this way. Now, what do we do with this? So here's my common denominator. This is what my answer is going to have in it. How do I get a numerator?
You multiply the 2.
So let's multiply that. That gives us 3x squared plus 9x instead of that. Okay? Multiply this.
Then you multiply this and
4x plus 8. Now you need to combine that term with that term. And furthermore, and this is really important, I'm sorry I put it out of order because it needs to be in primary order. Let me erase all this stuff because it's getting in the way. I need always to put a parentheses around this. The reason I do is because of this subtraction sign right there. If I do not put a parentheses around that, I'm going to get the sign on my constant wrong. Notice that by putting a parentheses, that plus 8 turns into a minus 8. If I leave the parentheses off, and you know, there were never parentheses there in the first place, so it's really easy to leave them off. And then you think you end up with 3x squared plus 9x minus 4x plus 8, and that's wrong. This negative sign has to be distributed to both terms. So you end up with a minus 8. And the easiest way to do that is by putting parentheses around that numerator. And it's one of the more difficult things to do in math because they weren't there in the first place. In other words, they were never there. I had a 4x or something like that in that numerator. So once it turns into two terms and that is being subtracted from the previous fraction, always put parentheses around that. Now, I still can simplify the numerator. I got a plus 9x and a minus 4x, so that combines to plus 5x. Now, one might ask, is it worth trying to factor that numerator?
No.
Well, what if one of the factors was one of those linear factors in the denominator? Then I could cancel it out and I could simplify it tremendously. So I've spent 8 years tutoring, and it probably for the first 6 years, I always tried to factor that numerator, just hoping I would come up with an x minus 3 or an x plus 3 or an x plus 2. But notice that none of those can be a factor if we have a minus 8 there. No, can't do. I might be able to get an x plus 2 out of that. Let's just, I'm going to say the only reason I gave up trying is because I never ever found a situation where I could get something. Well, I know what the only possibility would be x plus 2. So this would have to be minus 4. Does that give me that middle term? No, it does not produce a 5x. What if I had a 2 there and a 4 there? That doesn't produce a 5x either. So once again, I've come across a situation where that thing never factors. In other words, it factors using the quadratic formula, but it never factors to something that gives you a linear term that you can cancel.
Okay.
And so in the interest of speed, I generally stop when I get to there. Although that's not to say that some teacher somewhere couldn't dream up a problem where the numerator now factored such that one of the factors could cancel with the bottom. But it would be the first time in 8 years. Now before we go on, I want you to tell me what this is. In other words, the problem we just did is structured in a way that, boy, any time you have something that's the same, in other words, let's say I had this. And it's over x minus 7 times x plus 2. Well, I'm always doing this, right?
Yeah.
Okay. And the general rule of thumb is that you can only do that if they're exactly the same. Well, that's not actually true. The truth is that this is always equal to minus 1. The general rule is this: a minus b is always equal to the negative of b minus a. And you can prove that. Distribute that negative sign and you end up with negative b plus a, which is the same as a minus b. Okay? Which means that whenever you have an a minus b over a b minus a, you're looking at negative 1. And that's what that is a minus b over b minus a. So when you're looking to cancel linear terms, don't forget this one. Because every now and then they'll give you a hard problem where that's thrown in. And you have to know that that turns into a negative 1.
Okay.
All right, let's see. Let's have a look and see if we have enough time to do it. No, we don't. Well, we know where to begin next time, with K. Okay?
Okay.
Okay? So, what is this? It's 20K. Yeah, these are plenty difficult. In other words, yeah. I'm not sure why A and B are missing, but I think we'll follow this to the end. Because so far, any problem I've looked at that's missing from this is on the highest end of difficulty. And not that I mind doing those, but we'll wait until we need problems to do before we do them.
Sounds good.
All right. Talk to you tomorrow, I think.
I have no idea, but
Let me just remind you. Let's pull up my calendar. Tomorrow, Monday at 7.
okay.
I will be texting you a meeting ID number. All right, Nicholas. Talk to you tomorrow.
All right.
Bye-bye.
Yeah.